Okay, we'll get started. Welcome. Thank you for attending. This is the 534th Brookhaven Lecture. We're very excited for that. This has been going on since 1960 when Gertrude Schaff Goldhaber started, I'm losing my words here, started the seminar, and we try to have them every month. We have them set up for next month and the one after. I'm Ernie Lewis, the Brookhaven Lecture Committee Chair. Rong is going to give a lecture today. I'll introduce Jamie, who will introduce him. I'd like to thank Rong for all the hard work he put in. Brookhaven lectures are very different than typical lectures. It's supposed to be a lecture for the general audience of Brookhaven, all the scientists, which means it's not just people in your particular field. And this is a challenging effort for a lot of scientists to present their work in a way that's accessible to everybody. And they do a lot of work, so I thank him for his time. I'd also like to thank the committee and his department for the practice sessions. The committee volunteers their time to make comments and look over the talk and do so we thank them also. Please turn off your phones. They're recording this now. There'll be questions and answers after the talk. We can do it here, and if you're online, there's a question and answer button on your Zoom. Just hit that and I will call you afterwards. And we're going to dinner after this. If anybody would like to join us, please let me know. With that, I'd like to introduce Jamie Dunlop, who's Associate Chair of the Nuclear Physics Department. He's going to talk about how nuclear physics fits into the bigger picture of Brookhaven, and then how Rong's work fits into the physics department. So thank you. And then he'll introduce the speaker.
Hi, everyone. Yeah, I'm Jamie Dunlop. I'm the Associate Chair of the Physics Department for Nuclear Physics, which means that I'm responsible for the nuclear physics component of the Physics Department, which is about half of the nuclear physics, of the Physics Department's activities. The other half is in high energy physics. Now, the bulk of that nuclear physics piece is currently devoted to physics at the Relativistic Heavy Ion Collider. RHIC, the Relativistic Heavy Ion Collider, started running back in 2000, 24 years ago. We're in the middle of run 24. And I was just at a reunion this past weekend, and I was asked a number of times, what do you do? Tell me what you do and why it matters, right? And my elevator speech starts off with, at RHIC, we recreate the conditions as they existed a microsecond after the Big Bang. It's a piece of matter that sits in the extremes, trillions of degrees, magnetic fields, 10 to the 18th times the size of the magnetic field of the Earth, vortices, rotations, which are something like 10 to the 5 larger than anything measured before, makes a tornado looks like it's sitting still. Right? So it's a very extreme set of conditions. We're trying to look and see what happens to matter at those conditions. There's something very special about the conditions that we created, Rick, in that they're right near the transition between normal matter, the thing that produces all of the weight of everybody in here. 99% of the weight of matter is inside the atomic nucleus, which is made out of protons and neutrons, and those are made out of quarks and gluons, right? And so what we can do with the extreme conditions at RHIC is to melt the protons and neutrons, free the quarks and gluons. That was originally what we set out to do. We spent 24 years doing it. We're still doing it for the next year or so. And we build these gigantic experiments to make measurements and understand the properties of this quark-gluon plasma. So that turns us now to Rong. Rong graduated from Yale University with a PhD on jet measurements in proton-proton and lead-lead collisions in HALIS. There are two colliders in the world. Or two hadron colliders currently in the world. There's one in Switzerland, and there's one here on Long Island. Rong started off being trained at the one in Switzerland and then came here to do his work, and we're very glad that he came here to do his work. So he started off as a postdoctoral fellow, quickly became a Goldhaber fellow, and has risen through the ranks as an assistant physicist, an associate physicist, and then from January 2023 onward, he's been a physicist in the physics department. He's gotten a number of fellowships and awards, and sociologically, these large experiments that run at RHIC are very large collaborations, something like 700 scientists or so currently in STAR, and there's a whole management team in that. I was in the management team when I got out of graduate school and was in my first set of jobs. Rong was the analysis coordinator in the management team, making sure that all the results that come out of this gigantic experiment are correct and impactful. So he's had a huge influence. But let's hear now about the science that he's been personally working on at.
Thank you for Jamie for the nice introduction, and of course, thanks everyone for coming. So the title of my lecture today is called "Peeking into the Hot Quark-gluon Soup" with a pair of heavy quarks. For some of you, this might not mean much at this point, and hopefully by the end of my talk, the situation can change. So of course, we live in a complex world, and a natural question: what are the kind of the fundamental building blocks of the universe we are living in now? So let's take water as an example. So on the left-hand side, so here is a picture of water. If you can look into the water, what you see are the molecules which make up the water. So what happens if you look further into the molecule? What you can see is you will see an oxygen atom and two hydrogen atoms. So these are make up the oxygens. Of course, we can look even further, right? So if you look even further into the oxygen atom, so one thing you can see out, like only kind of outside of the larger radius, these are the electrons which are like circling around. Of course, you can look into the center of the oxygen atom. What you see are what we call a nucleus, which is made of protons and the neutrons. So of course, we can look even further. There's no reason we should stop here. So if you look even further into the proton, for example, what you can see is you will see 3 quarks, which are denoted as 3 balls here. And there's also like strings that connect the quarks together, which we call them gluons. So you can think of gluons as like the rubber band, which kind of binds all the quarks together and makes the proton. So these are the quarks, gluons, and the electrons. These are what we call the fundamental blocks that make up everything you see in the universe. So then we can look further, start a bit more. So there are in total 6 types of quarks. We call them up, down, charm, strange, top, and the bottom. And we usually use the first letter of the name to denote the quark. For example, we call this a U quark, it's up quark, or D quark with the down quark. That's what we saw in the proton. Actually, so for most of the visible universe today, they are mostly made up of up and down quark. And for the other 4 types of quarks, charm, strange, top, and bottom, usually we need to create them in specific processes, which we'll talk about more later. As I mentioned earlier, since they are fundamental blocks, which almost by definition, there's no internal structure, at least as we know now. Maybe 50, 100 years later, things will change, but that's our current understanding of these. And another kind of the property of these quarks are they have different masses. Actually, the size of the balls I draw here is roughly proportional to their mass. Because as I said, they are all point particles. There's no internal structure, so usually we view them as the same size. I use different size to indicate a different mass. So we usually group them in 2 groups. So the up, down, and strange quark, they are light quarks because they have a small mass. Then we also have charm bottom and a top quark. We call them heavy quarks, because they have heavy, large masses. And in this lecture, I will focus mainly on the charm and the bottom quarks, which are the heavy quarks. So quarks also have anti-quarks, which are the antimatter of the quarks. We call them anti-up, anti-down, something like that, anti-top and anti-bottom. And we use a bar on top of the name to indicate it is the anti-quark. So the U bar, we call them anti-U quark, and in the C bar, we call them anti-C quark. So at the beginning, I also mentioned that you can view gluons as a rubber band, which bonds the quarks together. So, and more scientifically, what we can say is these quarks are bound with something called a strong force. So what is a strong force? So we can start with something we're more familiar with. So we start with what we call the electromagnetic force, which is actually responsible for kind of binding the electrons in the nucleus into an atom. So for example, if you put an electron and a positron. So the positron is an antimatter of the electron. So they share the same mass, but they have a different electric charge. If you put them together, there will be electromagnetic force happening between the electron and the positron, which is actually the attractive force. They attract them together. And the way this force is realized is by exchanging photons or gamma between the electron and the positron. So this is what's happening in electromagnetic force. So strong force is something similar, but not exactly the same. So for strong quarks, strong force, it acts upon the quarks. For example, if I have a U quark and a D quark putting together next to each other, there will be also an exchange of the gluons between the two quarks. And this exchange of the gluon will realize the strong force between the U quark and D quark. So similar to the electron and positron case where they carry the electric charge, the quarks also carry something called a color charge. So there are three types of color charge. It's a red, blue, and green. Of course, have nothing to do with the real color we see. This is a special feature. We just give a name to visualize. So to summarize, so for the electric force, we have two charge, positive and negative. And for the strong force, we have three charge, red, blue, and green. So because of charge, so you can see that there's some similarity between the strong force and the electromagnetic force, but there's also very important distinction between the two. That's something called the color confinement. For the electromagnetic force, you can find isolated electron, for example, experimentally. However, if you think about that, the strong force, there's a particular feature called color confinement, means the quarks or the colored objects are always constrained within colorless composite particles, meaning the quarks always combine together to make a particle which exhibited no color at all. That's what we can observe experimentally. In other words, the quarks can never be individually observed experimentally. So because of that, I can give you a few examples how this happens. For example, we mentioned about proton and neutron, which make up all the nucleus we introduced earlier. For the proton, it can make up two U quark and D quark, and the three quark can carry red, blue, and green. And the mixture of three color, we call them the color neutral or no color at all. So the same thing can happen for the neutron. You can have two D quark and a U quark, and they can again carry red, blue, and green colors. So that's one way we can make colorless particles. And another way we can do this is we can combine quark and anti-quark. For example, we can combine a charm quark and an anti-charm quark to make a particle called a J psi. So the charm quark, for example, here it can carry a color red, and the anti-charm quark can carry what we call the anti-color, and the color and the anti-color can kind of annihilate with each other and make a colorless particle. So as we mentioned here, so we will never be able to observe quarks individually. So how do you know they exist? Actually, so this quark model, actually, Brookhaven made a strong contribution for the adoption of the quark model. So this is in 1974, a professor, Samuel Ting, from MIT. He did experiment at Brookhaven. At that time, we had this accelerator called an alternating gradient synchrotron. So here, so you can do a Clyde experiment and a discovery of a new particle, which is called a J psi particle, as we mentioned earlier, is made of charm and anti-charm. And that discovery of that new particle really make people believe that the quark model is the right model to describe all the particles we see. And at the same year, another team at Stanford, led by Burton, and they also discovered the exact same particle. The two papers are actually published back to back in the same issue of the journal. And this discovery of this new J psi particle was made in 1974, and they were awarded the Nobel Prize in 1976. This is probably one of the shortest span between the publication of the work and the awarding of the Nobel Prize, I think. And because of significance of that, and it was referred to as the November Revolution at Brookhaven. And experimentally, so what actually they measure is the electron and positron from the J psi decay. That's the measurement done by Sam's team. And the J side, because of the finite time, it can also decay to a mu plus and mu minus. So you can view muon as a bigger brother of the electron because they have almost the same properties, but the muon have a bigger mass compared to the electron. So with this deconfinement, that's what kind of a ubiquitous feature of our universe. So then a question you may ask is, can we actually deconfine matter? Can we make the quarks and gluons to move freely, right? If you think about, you can boil water in a kettle. So if you keep on boiling it, at some point when the temperature rises to high enough, then you will see steam coming out of the kettle. So if you look kind of in microscopically further into this process, what it does is, if you can boil the water, what it does is you can break the connection between the atoms, between the molecules, and the molecule can evaporate, and then they can move much more freely in the steam compared to when they are confined or constrained in the water. So can we do something similar for the quarks and gluons? So what's the idea is, can we actually also heat up, say, the proton or any other nucleus you can think of, and it can freeze up those quarks and gluons, so they can move almost freely, so we can make a deconfined matter. So as actually Jamie mentioned at the beginning, actually it turned out we can. It's actually already happened before. So if it's a Big Bang, which is our current theory of our universe. So it happens, let's say, at t equals 0. And that's when the universe is at a very high temperature, very high density, and at a very high energy, right? So we believe that about 1 microsecond after the Big Bang, the universe is indeed in a state that the quarks and the gluons can move almost freely. Then, of course, the universe will keep on evolving, cools down, and make up the world we see now. For example, 9 billion years after the start of the Big Bang, we think the Earth was formed, and of course, 13.8 billion years later, that's where we are now at Brookhaven. So this is the picture of the Brookhaven. So this particular state of that, where the quarks and gluons can move almost freely, we call them quark-gluon plasma. So this is a normal state of matter, which is made of defined quarks and gluons. Is defined meaning that they are not confined into the colorless particles anymore. So that's why we refer to it as a soup of the quarks and gluons. We can move like freely in a soup. Then I think, of course, starting this, of course, is interesting in itself. Then we'll ask, does it have a more kind of impact on kind of our understanding of other stuff? For example, so why do we want to start the quark-gluon plasma? So one of the biggest reasons is we want to understand properties of the matter under extreme conditions. For example, at high temperature, which it was the case at the early universe, right? When the temperature was very high, that we want to know how the matter evolves, and hopefully that can help us to also understand the evolution of the universe. On the other hand side, it can also probably help us to understand the matter on the high density, which is the case for neutron stars. That's also another very hot topic in astrophysics. So starting this, of course, does have like a long impact or high impact in other fields as well. So with all this like a good motivation, then the next question is, how do we actually do this? How do we actually access quark-gluon plasma? Of course, we don't have a time machine to travel back in time to look at how the universe looked like at the very beginning. So then we would naturally think, can we make this in a lab, right? So this work was also was kind of proposed by T.D. Lee, who is also kind of closely related to Brookhaven. He won a Nobel Prize in 1957. He actually worked as a guest scientist at Brookhaven in 1956. So in 1974, he gave a talk at Berkeley where he said that we should investigate some bulk phenomena by distributing high energy over a relatively large volume. So the fact that this direction has never been explored should by itself serves as incentive for doing such experiments. So this kind of the motivation or this idea from him was viewed as a birth of the heavy ion physics, because the key of this is his idea is we want to distribute high energy. So meaning we should we should accelerate the particles into high energy and in a relatively large volume. So then a volume much larger than proton. So you have enough space for the gluons and the quarks to move around. So that's why we need heavy ions or large nucleus to do such experiments. So of course, since 1974, when he brought up the idea, people have been doing like such experiments at a different facility. But it wasn't until 2000 when the RIC was turned on that this field really see a significant advancement. So this is what Jamie also introduced at the beginning. So here at Brookhaven, so we built a relativistic heavy ion collider, which started its operation in 2000s and is still operating today as we speak now. We are still taking data. And so in this particular collider, so it can collide the gold ions, so which is what we call the heavy ion, because the gold nucleus have 79 protons and 118 neutrons. So it's much bigger compared to proton. So we have enough space for the quarks and gluon to move around. And also we can, the named relativistic, meaning it will be accelerated to almost to 99.995% of speed of light. So we'll acquire a lot of energy. So the process goes like this. You start with some sources like a gold ion source. And it will be accelerated in the booster, then we'll go to then will be accelerated again in the AGS, which we mentioned earlier, where the JSON was discovered. So in the AGS, as I said, so these gold ions are further accelerated, they will be injected into RIC, the relativistic heavy ion collider. There are two rings at RIC. One is called the blue ring, one is called one is the yellow ring, and the one is the blue ring. So what it does is we will have the opposite traveling beams into the two rings, and at a certain point, they will collide with each other, and they will hopefully make the Quark-gluon plasma. So that's how this the relativistic heavy ion collider works. So what happens once you have a gold-gold collisions? So this is a schematic view of this collision. So we will start with the initial. So we're coming with the gold ions coming in like here. Then you have the initial collision and the QGB is formed. So that's what we are trying to understand in terms of the property. Of course, then the QGB will keep on extending and cools down. And then you will have all sorts of kind of what we call the composite particles. So that's the only thing we can observe experimentally. There's colorless particles coming out of the collision, and it can be measured experimentally. That's what we actually get. So what we do is we measure what we can get when we try to understand the property of the quark-gluon plasma, which is what we really the goal of this. Because of this kind of the evolution of a heavy ion collision is actually similar to the evolution of the universe. Sometimes we call this the little bangs. So then with all these like gold collisions, which we expect them to create the quark-gluon plasma. So actually, how does quark-gluon plasma actually look like? So here I just kind of compare the quark-gluon plasma with the human and the sun in three different ways. First of all, let's compare the size. Let's say a typical human have a size of 1.8 meter, and a sun has a size of 1.4 billion meters. And QGP is actually have 10 to the minus 14 meters. You can see the proportion between the QGP and the human is actually even smaller than the proportion between the human and the sun. I think I forgot to. I should have a laser pointer. Okay, so you can see the QGB is extremely small. And in terms of lifetime, let's say a human can live up to 100 years. Let's just be generous. A sun can live about like 10 billion years. However, a QGP, the lifetime of QGP is only 10 to the minus 2 seconds. You can see the lifetime is so much smaller compared to what a human can live, for example. On the other hand side, it's extremely hot. So let's say a human have a 36 degrees Celsius and the sun have a 10 million Celsius. And on the other hand side, the temperature of the QGB, we think it should be at least 2 times 10 to the 12 degrees Celsius, which is almost 1 million times more than the center of the sun. So this particular QGB is something that is very small. It has a very short lifetime, yet it's extremely hot. So it's a very special type of matter that we really want to understand its property. Then the question is how do we do this, right? So you have this particular matter, so how do you actually study its property? There are typically two ways you can do this. So one way is you can observe how it behaves collectively. So as I said earlier, so experimentally, we can measure the particles coming out of the collision. And from that measurement, if you observe all the particles, you can infer how the Quark-gluon plasma behaves collectively. So for example, you can observe how easily it can float. You can think of a honey, if you, as you know, so the honey, if you pull out the honey, then the honey flows very slowly, right? So that's why we call they have a large viscosity. If you compare honey to water, the water flows much, much easier, right? It flows faster, much smoother. However, if you look at the QGP, what we know about the QGP is actually flows even smoother than the water. It flows almost with no resistance. That's why we call this almost like a perfect fluid. So that's one way you can study the properties of the QGP. Another way is to put some external probes to see how the probes behave in the QGP. For example, if you think about you have a cup of water, if you drop two sugar cubes into the water, will they stay or they will dissolve, right? So the result of the staying or dissolving will reflect the properties of the water. So can we do something for the QGP? If I have a soup of the QGP, can we drop something inside and see whether this will stay or this will dissolve? So then we can come back to our old friend of J-psi. So actually, so we can do what we can do is we can drop J-psi into the QGP. However, as we said earlier, the QGP is extremely has an extremely short lifetime. You cannot like exert J-psi from outside. It has to be produced also in the go-go collisions. Actually, it does. It's because of it's a very high mass. The J-psi can be produced in the go-go collisions before the QGP is formed. So then naturally, then they will go into the QGP. Then we can observe how it behaves. So then experimentally, theoretically, what's our expectation? So we expect that the J-psi can dissolve or melt in a QGP, which actually, for more than 30 years ago, this kind of signature was proposed as the evidence for the QGP formation. So how exactly this process goes? So we start with the QGP, we start with the J-psi in the vacuum. Say you have the J-psi here, you have a charm and anti-charm quark and a gluon. And you have the vacuum that's basically nothing around. So the J-psi stay as it is, which is good. If you start to put the J-psi into a Quark-gluon plasma with low temperature and low density, so of course you have these free moving quarks and gluons, which occasionally bounce around or bounce off the J-psi, and the J-psi you can still see the J-psi. That's good. However, if you keep on increasing the temperature of the QGP, and which also increase the density, then these quarks and gluons can get inside your J-psi, can get in between the charm and the anti-charm quark and break the string or break the binding between the charm and anti-charm. So what this will do is you will what we call deconfine or melt the charm and melt the J-psi, so end up with a charm and anti-charm quark that also move almost freely as other quarks and gluon. So what does this mean? So if we expect this, can we see what does this mean, or how do we observe this experimentally? So in the end, this is basically a counting experiment. So because of this this melting of the J-psi, experimentally we expect a reduced production yields of the J-psi particle. So what does this mean is if I have a QGP produced here, then if I have a few or let's say 3 J-psi also produced in the same go-go collisions, so how many of J-psi will survive, right? So will the J-psi melt, or the J-psi will stay at the J-psi and be observed experimentally? So essentially, you just count how many of them they will survive. Of course, for any experiment, you need to quantify this. So the observable we use to quantify the suppression is called the nuclear modification factor, RAA. So this is used to quantify the level of the J-psi suppression in go-go collisions. So what you want to do is the RAA is defined as your J-psi yields after you're going through the QGP divide by the J side yields before you go into the QGP. Right? So if you say, okay, half of the J side survives, you expect the RAA to be around 0.5. Of course, we cannot measure J side before they going through the QGP. As I said earlier, so QGP is extremely short-lived. So we cannot say when the J side stop producing, we say, okay, stop. Now we measure J side, then we use, okay, we resume the QGP, then we see how many J side survive. We cannot do that. What we can measure is how many J side we see after they go through the QGP, right? Then we need something to tell us if there's no QGP, how many J side would there be? So that's how we do this. What we actually can measure is the J side yield in the go-go collisions, and we use the J side yield in proton-proton collisions as a reference because we don't expect the QGP to be produced in the proton-proton collisions. And then we properly scale them such that if I say CRAA less than 1, that means a suppression of the J side yield. If I see RAA larger than 1, it's an enhancement of the J side yield. So that's our kind of the observable we measure experimentally. Now we have all these ideas. We have brick to produce QGP. We want to drop the J side into the QGP, and we do have them in the go-go collisions, and we want to measure how much it survived or the nuclear multiplication factor. And of course, we need a detector to do so. And that's where the star detector comes in, and that's where I personally work on. So this is a layout of the star detector. As I said earlier, there are 2 beams of the gold coming in. So you have the beam of gold coming on one side and another beam of gold coming on the other side, and they will collide at the center of the star experiment, and then a QGP is produced, which is all good. And on the other side, as I said earlier, a J side could also be produced in the go-go collisions as we see here. And as I mentioned earlier, so because of J side has a finite lifetime, it will decay very fast, and it can decay in 2 channels, decay into either a electron-positron channel or decay into a mu plus and mu minus channel, as I also mentioned earlier. So this, here, for example, you have the J side produced in the middle, and you have the mu minus and the mu plus and the mu minus from the J side decay. So this particular channel is what I'm particularly interested in because we actually built a specific detector to measure the muons. So this is what we call the muon telescope detector, which you can see as a white kind of white blobs here. It's actually at the very outside of the star. So if you ever have a chance to go to the star, you can actually see them with no problem at all because it's the very last outmost layer of the star. So this is the detector actually I have been working on since I joined Brookhaven 10 years ago. So that's both a special place for me. So what really happens is you have a J side, they decay to the muon, and muon will fly through all the layers, different layers of the star detector. And in each layer, they will leave a signal or a hit, we call. And from all these hits, we can reconstruct the muon and we can measure their momentum. So then with that, we will try to get to the J side. Of course, you will ask, right? So because there are also many other sources they can produce muons. So how do you know that's just from J side, right? Because if you measure muon, there's no kind of indicator say, oh, that's a muon from J side. We don't know that. So how do we actually do the measurements? So what we do is we pair the positive and the negative muons, and then when we calculate the mass of the pair using the momentum of the decay, the daughter pair, and this is the mass distribution for the muon pair. You can see the data, which is shown at the black points here. So the peak here, that's our J side peak, because for any muons coming from the J side, it will have a distinct peak around the J side mass range. So that's how we know that's our J side. And there's also a background component, which is shown as this blue histogram here. This is almost like a very smooth distribution because again, there are other muons from other sources. So usually we call them backgrounds. So that's the way we can distinguish a muon pair from the J side decay or a random muon pair from other sources. And from here, we can measure how many active J side are produced in the go-go collisions. As I said earlier, then we can compare that to the proton-proton collision. and see how much suppression we observed experimentally. So the results are shown here. So actually what in the end, what we measure is the J size suppression factor, RAA, is about 0.35. This is one measurement that I actually personally did myself. And we published the results in 2019. And so with RA about 0.35, meaning about a third, only a third of the J size survive the QGP. In other words, if I start with 3 J size, and once they go through the QGP, only I can observe one of them. So this kind of the suppression or melting of the J side, as I said earlier, is a strong evidence of the QGP formation at RIC. So this is all good, right? So we start with this idea of the J side melting. We see that. So as a matter of fact, there are actually many other different quark-gluons. So the J side, we call the J side is one type of what we call charmonium, which are made of charm and anti-charm quark. There's another type of charmonium is called a Psi 2s, also made of charm and anti-charm quark, but they have a larger size. That's because they are in different energy status of the charm and anti-charm pair. That's what we call the charmonium family. There's also a bottomonium family. As I said at the beginning, there's the heavy quark, we have the charm quark, and they have the bottom quark. So there are 3 types of charmonium I will discuss later. We have epsilon 1s, 2s, and 3s. Again, all of them have the exact same quark content, which is a bottom quark and an anti-bottom quark. But they have a different size because they are at a different energy stage. So if you recall what we said earlier, because the melting of the J side in the QGP, that's the interplay between the quark-gluon size and the QGP temperature, right? So you can imagine that a quark-gluon of a larger size will be easier to be melted because the free quarks and gluons in the QGP, it will be easier for them to get inside into the quark-gluon and break them up. Also, as I said earlier, the higher temperature, it will be easier for the QGP to melt the quark-gluon. So with the 5 different quark-gluon, the J side, Psi 2s made of charm and anti-charm, and the epsilon 1s, 2s, and 3s made of bottom and anti-bottom, we can actually use them as a thermometer because they have a different melting temperature, right? So from the Psi 2s to the epsilon 1s, so they have a decreasing size, and the melting temperature will become higher and higher. So now, in other words, the Psi 2s have the lowest melting temperature, and epsilon 1s have the highest melting temperature. So then with this, so how do we exactly use all these quark-gluon to probe the QGP? So let's go back to our early example where we have the water, and we drop the sugar cubes into the water, and we see how they dissolve or how they stay. So there are 2 ways we can actually kind of do a variation of this process. In one way, we can actually drop different things. Other than the sugar cubes, we can drop, for example, coins into the water, and then naively we think, okay, the sugar cubes will dissolve and the coins will stay. And that, again, by comparing the different behaviors of different kind of the probes, you can also infer the property of the water. Another way is you can drop your sugar cubes in hot water. They will think, okay, then these sugar drops cubes will dissolve faster in a hot water. So can we do something different, similar for the QGP? So in one way, so as for this the sugar and the coin, we can drop different types of quark-gluon. As I said earlier, we have, for example, the 3 epsilon states. We can drop all of them into the QGP of a given temperature profile. And what we expect is epsilon 1s, which is the smallest size, and epsilon 3s, which is the largest size, will melt much more easily compared to the epsilon 1s, which have the smallest size. So that's what we actually measure. So this is our results is for a QGP of a given temperature profile, then we can measure the suppression or the nuclear modification factor for the 3 different epsilon states. So this is actually, there's a humongous amount of effort went into this result we published last year. So we actually analyzed 4 years of the data where we scanned over 160 billion gold collisions. And with effort from myself, a postdoc, and 3 students together, we were able to pull off these results. This is for the first time we can actually measure the suppression of the 3 upsilon states separately at RIC. As I said earlier, if you go from right to the left, the size of the upsilon increases from upsilon ys and 3s. And as expected, your RA value also decreased. That means your melting also increasing. Again, so this confirms our expectation that a larger size of the quarkonium will melt easier, or you will see more melting in a QGP than a quarkonium of smaller size. So that's one way we can use this thermometer idea. So, and then you can compare to a theory that suggests that the QGP temperature is actually should be above 3 times 10 to the 12 degrees Celsius, which is larger than what we said earlier. Another way we can do this is, as I said, so for the sugar cubes, you can drop in hot water and the cold water. So can we actually change the temperature of the QGP, right? If I just look at one quarkonium of a given size, we expect it will melt more easily if the temperature of the QGP increases. So how do we change the quarkonium QGP temperature? The way we do this is to look at the different types of the collisions. You can imagine that there is something we call the peripheral collisions, where the 2 gold nuclei just glance through each other. So like on the tip of here, so the overlap region is very small. So we expect the QGP produced in those collisions to have a low temperature. If you increase the overlap region between the 2, you will see the mid temperature, and in the end, you have a head-on collisions, you expect to see a high temperature. So by looking at the surviving pattern or the surviving probability of a given quarkonium at a different collisions, we will see if there are suppression changes. So the results are shown here. So here we pick one quarkonium, is the upsilon 2s, and then we can look at how the upsilon 2s RAA changes as a function of the QGP temperature. So from the right-hand side, this is the head-on collision with the highest temperature, and this is the peripheral collision with the lowest temperature. As you can see, as the temperature of the QGP increases, and the suppression also increases. Again, so this is another way we can use quarkonium to look at the temperature of the QGP. So what have we learned so far? So from all the J psi and all the quarkonium suppression, we found evidence that the QGP is indeed formed at RIC. And by comparison to the theoretical calculations, we infer that the temperature of the QGP should be above 3 times 10 to the 12 degrees Celsius. So this is all good. But what's next? Is there anything more we can do? As we said earlier, the QGP actually evolves. So the temperature of the QGP actually starting with a high temperature and actually cools down. So can we actually map out this temperature profile? To do that, what we need more quarkonium states with a much better precision as we have now to constrain this temperature profile. So if we can put together all these RAA measurements for different quarkonium states, from upsilon ys, J psi, upsilon 2s, and upsilon 3s, from right to the left, we have increase in size, and you have the increase in suppression. One thing you can see that we actually don't have any measurement of the upsilon 2s, which is at the smallest melting temperature. That's because it's actually quite challenging. We don't have enough statistics to do that, so we need more. On the other hand side, we can see the upsilon 3s and the upsilon 2s actually have the measurements still have large error bars. So we need a better momentum resolution to find those peaks, and also we need more statistics to increase our precision. As a matter of fact, you can see here the upsilon 3s, we only have an upper limit. We don't even have a real measurement. So as Jamie mentioned, so we are taking data until next year. So starting from 2023 to 2025, the main kind of the goal of the RIC running is to collect unprecedented statistics for both the gold and the proton-proton, which we need as a reference, with both the star detector and a brand new S-Phoenix detector. So with this improved, enhanced statistics and improved momentum resolution, we expect to have a much better the Quark-gluon measurements from the experiments. Of course, as I said, so our data taking by schedule will end next year, and we will have another probably 3 to 5 years of data calibration and data analysis. Then we ask, so what happens afterwards? After 5 years, so what do we do, right? So of course, we know the EIC will be built at the Brookhaven, and so this is a sketch of the electron-ion collider. So what the EIC will do is you will collide the electron, for example, with a gold ion. What we try to learn is the internal structure of the gold ion. So, but what does that mean for us? For example, the QTP study. So, because the structure of the gold ion, that's actually served as inputs for any kind of the understanding or simulation or modeling of the gold-gold collisions. You need to know where you start with to better understand what you end up with, right? So this better understanding of the internal structure of the gold nucleus will also help us to improve our understanding of the heavy ion collisions. So I think this also have a connection. That's what Brookhaven will do in the EIC to what we are doing now at RIC. So let me summarize. So we use Quark-gluon method extensively to investigate the QTP properties since the birth of the heavy ion physics. So hopefully today I gave you a few examples of how we do this. So I talk about J-psi and the different Quark-gluon states. And with the anticipated experimental improvements, we hope we'll get a clearer peek into the QTP through the Quark-gluon measurements. And in the end, I would like to thank the DOE Office of Science for supporting the RIC operation and the Brookhaven Star Group's research. I would also like to thank the Star Collaboration for providing me personally the opportunity to do the results I'm able to present to you today. And also many thanks to Joe, Ernie, Beyond Peter, Jassim, Prithwish, Lidran for their help in the preparation of this lecture. And of course, thank you everyone for coming today.
Thank you for a wonderful talk. That was very exciting. If you're online, please put your questions and use the button at the bottom of the screen. Any questions from anybody here in the audience? Yes.
Yeah, so
please repeat the question so everybody online can
So
hear
the question is what's the benefit to start the gold nucleus with the electron, right, with the EIC? Right, that's what I was saying. So we don't expect the QTP to be produced at the EIC, but what are we trying to learn from EIC is what's the internal structure of the gold nucleus look like, right? So from there, you can think of that as basically as an input for any heavy ion simulation or any heavy ion collisions, right? You need to know where you start with, then you do all the evolution, then you have the QTP produced, right? So I think that's where the connection comes from.
Any other questions? Yes.
Well, so we do.
Can you repeat the question?
Sorry. So the question is why heavy ion? Why not light ion? So we do. We are running. We can run like say oxygen, like light ions, but we start with the gold because we want to make sure we have enough energy to actually to cross the boundary to make the QTP to start with, right? Because it's not. I mean, you can start with a light ion, but I don't think it's guaranteed that the QTP will be produced. So you start with something we think you have a much better chance. Right?
Other questions? Yes. I try to summarize that. I should hand it the mic. No, try to
That's okay.
summarize that so the audience online.
So the
knows what-
question is, why we use proton-proton as a reference in the JSI year before they go into QGP, because the proton-proton and gold they are very different. They have different multiplicity, things like that, right? So that's why I put it, it's actually scaled. If you don't scale, so true, right? Even if there's no QGP in the gold, if you just simply compare the JSI producing a gold in the pure proton, naively you think that there will be much more JSI producing the gold, right? You have more. You can think of gold as a many kind of a superposition of the proton-proton, proton-neutron, neutron-neutron collisions, right? Even if there's new QGP, you have much more collision per gold compared to proton-proton. That's how we have a geometric scaling such that if the RAA, if there's no QGP effect, the RA will be at 1. So this is the scaling to make this RA at 1. So we have a kind of a good baseline compared to. So this is where this scaling comes from. Yes, indeed, what you say is true.
Certainly. Let me give you the microphone this time so everybody can hear.
So I read two papers before, like discussing that there should be a possibility for creation of quark-gluon plasma and proton-proton collision at LHC. So I wonder if going higher in energy, like 14 tera-electron volt, could give us a possibility for creation of quark-gluon plasma from proton-proton collision?
You mean the creation of the Quark-gluon plasma?
Yes.
Oh, yeah. I think that's a still a debated topic. So at LHC, as you said, a very high energy proton-proton at a high multiplicity, we see signatures that we used to think these are the kind of the signatures of the QGP. Like as you see, we see like flow signatures, things like that. But I think at this point, it's not settled that whether QGP is producing QGP or not. Maybe that signature, we used to think that unique signature of the QGP, maybe they're not. Or they might behave different or have a different manifest in proton-proton compared to gold. So we do see those interesting signatures, and I think a lot of people actually work on that experimentally and theoretically, but it's not settled yet whether the QGP is indeed producing proton-proton or not.
Any other questions from the audience? Any questions online? I don't see any, but let's thank our speaker once again. And if you're interested in joining us for dinner, please stick around afterwards. Thank you.